So did everyone finish the homework? Super easy, right? Yes, no? I guess it was more long than, I think probably more long than difficult, because there are really two parts to it. But hopefully it was a nice refresher on, or at least, reinforcement of what we've covered with pandas and plot visualization. Just some quick notes, some quick announcements before we begin. A lot of you were overwhelmed by last lecture. Well, I guess feedback from last lecture was very mixed. It was very polarized. A lot of people felt it was very intense and they felt overwhelmed. Other people felt it was a review. Some people felt it was just right. Overall, though, I think a lot of people felt a bit, I guess, intimidated by some of the notation and some of the concepts. So just to, I guess, clarify or make things clear. It's sort of one of the most difficult things about teaching this class is everyone has different backgrounds, and when you introduce math concepts or programming concepts, some people are familiar with the notation, some people are not. And one person asked, is the notation and the formulas, are they important or are they required? And the short answer is no. The long answer is that what's really important are the concepts. And the notation and the math and the equations are simply a means of communicating a concept. And really it's you don't have to necessarily know or understand or be able to derive the equations. The reason why I present the equations in sort of the mathematical form is that it's really, I guess, the standard form. And I guess that's also part of the reason why I spent a chunk of last class dealing with, I guess, sort of visualization and trying to, I guess, overlay the concepts of what error is and what regression really means from a geometric perspective on the board. Today's class, we're going to pick up right where we left off last class and basically review that material and sort of extend it to some new concepts and understand how we evaluate regression. But before I do that, I at least sort of wanted to clarify some issues on notation. And maybe not everyone knows what this symbol means. This is the capital letter sigma. If I declare an array, in mathematics, by the way, we usually write what we call vectors or lists with angle brackets. We don't use angle brackets in programming notation because they look like less than or greater than signs. But if I define a list and I say fill it with some numbers, again, we know that in mathematical notation, we just use the subscript as sort of an index. So x0 would be 2, x1 would be 3. This sigma, the capital letter sigma, just represents a summation. If I say the sum of x, and we introduce an iteration variable here from 0 to 2, this is exactly the same thing as 2 plus 3 plus 13. In Python, we would just write it, it's basically just a fancy for loop. Python syntax would be for I in range 3, and then it basically would have some sum total. So for I in range 3, it's exactly the same thing as saying total plus equals x. It's just a summation over a list, a summation over a vector. And this is what I mean by concepts are more important than notation. If you understand that the sum of some variable, if you understand that the operand of this sigma is just a summation of what's inside, it's basically just in what you would call an element-wise summation. So for each element in the list, I would be summing from the 0th index to the 2nd index. And if I changed my iteration variable here to 1, sort of generalize this, it would basically be x sub 1 plus x sub 2. And again, if I just sort of increase this from 2 to 2, it would just be basically summing over one item. It's just an iterative sum. The other, I guess, formula that I used was the beta notation. If I mentioned that when we're looking for regression, what we're trying to do is we're trying to find a line. And I described this line as y hat. And I said this y hat is equal to some beta, which is a parameter, times by an independent variable, plus some beta naught. And I called beta 1 and beta 0 the parameters of my regression. We call these the coefficients in the tools that we use in the class. But again, the fact that these are Greek letters, in math we use Greek letters so that we don't confuse. When we're talking about coefficients, we don't want to confuse our coefficients with our variables, and so we use really a different language entirely, a different alphabet entirely for talking about coefficients, just to keep things clear. In elementary school or whatever, they use ax plus b to represent parameters. But I can call x b1, and I can call the lowercase b beta sub 0. I can really call them whatever I want, but the convention is to use the Greek letters so that they don't get confused with the variables. And you consistently see that in nomenclature and in articles and so forth. So I use consistent letters in notation here. Questions on that? Pretty clear? Again, if you can understand the sum, if you can understand the concepts and what these equations represent, if you can visualize and understand really the big picture of what's going on, then it provides a lot of mileage towards really understanding the concepts. Another challenge with this class is that there's a plurality, a large diversity of tools that are used in the field for data analysis. If this were, say, a front-end web development class, life would be a lot easier because we'll be using HTML, JavaScript, CSS, and we could use HTML, JavaScript, CSS exclusively because no matter where you go, and if you're doing front-end web development, you're going to be using those three tools almost without question. Unfortunately, in data science, it's because it's old and because it has sort of a complicated history, there's a variety of languages, a variety of tools that are used. And so I want to be careful as an instructor and not sort of, I guess, overfitting, so to speak, and teaching you one tool or one process too closely. Because yes, Pandas is great, yes, Python is useful, but there are other tools as well. And they all sort of borrow from each other, and they're all relevant, and they all sort of have consistencies and patterns. But my point is that you shouldn't memorize or really focus too deeply on how to do something. You should focus on why it's being done. What's the reasoning behind it? You'll start to see as we go through this class, you'll see certain patterns. In fact, maybe you've seen that already, where you see certain tools and certain commands that I'm using in class that were used in, say, the homework from the Harvard lecture that you had as your first part of your homework. So you'll see these sort of reusable patterns. And as you start to use, as you inevitably use other languages, other tools, be it R, be it Spark, or whatever, you'll see the same nomenclature, and you'll see the same concepts being reused. And so really my emphasis is to teach the concepts and to teach the basis for this stuff, rather than focusing too much on pandas and too much on the functions and too much on the specific implementations of the tools we use. Having said that, the agenda for today, last lecture was a little bit more theory, a little bit more lecture than practice. Today we'll be taking what we took last lecture, and we'll actually be working through those examples, and we'll be playing around with it interactively. But I urge you to, in all of the exercises we do in class, play around with them, fiddle with them, change things, break things, really see what happens when you change certain variables, because that's really how you learn. I can always show you, it's not easy for me to show you how to do something. It's not difficult for you to copy what I'm doing, but learning, like anything else, is an active exercise. And some of you who are overwhelmed, I think to an extent that's a good thing. It's good to be outside of your comfort zone, and it's necessary to be outside of your comfort zone in order to learn. If, on the other hand, you feel as though you're completely lost and you feel as though you're behind on something, if there's some gap that's missing, reach out to us on Slack. Feel free to ping us as much as necessary, and we'll accommodate you to the largest extent possible. On the flip side, there are others of you in the class who are frustrated, who feels that the pace of the class is too slow, and that the material is, I guess, too rudimentary. And conversely, on that point, reach out to us as well, as we can accommodate you. And there's a lot of interesting stuff. And the great thing about General Assembly is that it's a community, and there's a tremendous amount of resources out there that we can share, and that we can help you tailor the curriculum and tailor really what you want to get out of this class to the greatest extent possible. I don't want anyone to sort of feel, and I'm not saying this is the case, but I don't want anyone to feel as though they're not getting absolutely as much as they can out of this class. So I just want to state that and make that explicit, because moving forward, we're really going to pick up the pace. We're going to move more and more quickly, and I want to make sure that no one is frustrated or sort of left in the dust, so to speak, on this stuff. And having said that, now that we've at least sort of all gotten to the same page, or more or less on pandas and on Python, we will put those exercises in practice more and more in the class, and there's going to be more of an emphasis on live examples throughout the class. Questions, thoughts? Okay. So I'm going to start by going through. We'll start by sort of recapping last session. Something wrong with the slides, I apologize. We're basically giving a live sort of overview of the concepts we went through last class. I'm going to start my IPython notebook. By the way, usually when I run IPython, I usually run it in the base class repository. If I say navigate to repository, it just helps me, within the IPython notebook, I can then navigate to anything that any of the folders within the class. So we're on lecture 7. So this is the same, just to sort of quickly review last class. Last class we went through this advertising data set. And we talked about a few interesting features and characteristics of this advertising data set. And we were trying to define or understand or explore a relationship between amount of advertisement money spent on TV, amount of advertisement spent on radio, and amount of money spent on newspaper, and how that influences sales. And we started by, at a high level, visualizing our data set, sort of understanding the independent axes of our data set. And we described these three features, or these three dimensions of the data set, as being our features. So our hypothesis is, or really what the question we want to answer is, and we always start with a question, a hypothesis, before we do anything else. We want to understand what the relationship is between sales and amount spent on each of these channels. And qualitatively speaking, there is definitely a relationship between, clearly a relationship between amount spent on TV and amount sales. And there seems to also be a relationship between amount we spend on radio and sales. Newspaper is less clear. And we basically said that we're going to try to find a quantitative, an objective basis, what we called a model, that formulates a relationship between our independent variables, what we called our feature variables, and our target variables. And we did this through a process what we called linear regression, in which we were trying to find the equation of a line that best describes the data provided. And in this case, we did linear regression, so we had two sort of parameters. The objective of linear regression was to find two coefficients, beta sub 0 and beta sub 1. Beta sub 1 being the slope, the amount, really the degree of the relationship between our independent variable TV and our independent variable TV and the dependent variable sales. And when we run linear regression, really it's a process of finding beta sub 0 and beta sub 1. But we don't know necessarily, we can almost always run regression, but it's not always going to be, not all regressions are the same. Not all regressions are equal. Because if I do regression on the newspaper data set, then it's less, I have less confidence here than I do in, say, my TV data set. And again, we can see that, but we need to have an objective qualitative way of describing that. And we defined an objective qualitative way of describing that through varieties of feature, but we spent most of our time talking about a variable called r squared. And r squared we defined, so if we're given a set of points, in this case, this is a very simple example of what we call ordinary least squares regression. We have a set of points in x and y, and we're defining a model. Our model is this blue line, and we want to find the line that best fits that data. And quantitatively, we describe that as minimizing the amount of error between our data points, the specific points we have, and our model. Again, our model is just a line. Our data points are discrete in nature, and we basically want to find the amount of difference between the observations and our model. And the closer our observations are to our model, the less error we have, and we have a more accurate model. If, on the other hand, these points are spread out as randomly as possible, then the regression, the r-squared value, is going to be much lower. And so if the independent variable y is strongly explained by x, then our r-squared value is going to be close to 1. If there's a poor relationship between the two variables, then our r-squared variable is going to be close to 0. So an example of that, you can imagine if we took a shotgun blast and just randomly plotted points here, our r-squared value would be close to 0. Similarly, if we had a very, very tight line, our r-squared value would be close to 1. Quantitatively, we defined two key metrics in how we define these lines. We added each of these, what we call the residuals. We sum each of those up by subtracting our model, this is our y hat, from the specific observation and squaring it. And we call that the sum squared error of the residuals, sometimes called SSR. And from there we can use those variables those metrics to define the slope and the intercept of our line. Before I go too far, I want to show the method of solving this interactively in IPython. So make sure you start up your IPython notebook, pull down the latest, and this is the 07 linear regression under the lectures folder. And I am going to start a new project from scratch, so a new notebook from scratch. Some of you had questions or issues on how to find, when I call read CSV, when I read a file from the file system, some of you had questions on how Python finds that file. Again, I'm going to be working with the file I showed last class, and this is the advertising data we had here. And in the example last class, I grabbed it from the internet. I'm going to download this file just to sort of make this clear going forward, because it's easy to waste a lot of time on simple stuff like this, but it's also not that complicated. So I'm going to, within my environment, I'm going to download this data set locally. Again, last class I actually grabbed this directly using read CSV. I read it directly from the web at the URL. If I navigate to my DAT20 NYC folder, I am going to download this to my data folder. So I've just navigated to the data folder, which you all have access to in the course folder. I'm going to use a Unix command called wget, and this is basically just a means of downloading something from a URL to the current repository. And you can read about it if you call man wget. It'll show you all the documentation. And there's a bunch of flags and a bunch of settings, and most of which aren't actually that useful. But I'm going to say wget, and I'm going to just cut and paste the URL straight from my browser. It's this usc.edu gareth isl advertising.csv. And when I run that, it just does the download, does a transfer, and here I have it, this advertising.csv. And that is exactly the same as the, if I do head-n, if I look at the first 20 lines of that advertising.csv, you can see I have that same data. So it's just a quick way to download files rather than having to drag things around in Finder using the wget command. Now that I have that in my local data folder, I'm going to call read.csv. But again, read CSV, whenever I'm reading a file, and this isn't specific to pandas or anything like that, Python always keeps track of what's called a current working directory. And os.get current working directory, if you do print os.get current working directory, this is where Python, my Python instance, is loading files relative to. So this is a file on my computer. Again, it's just a linear regression up until about here. You guys all have the same path for the last few folders. But I can see if I look at where my data folder is, my data folder isn't in the lectures folder. It's in the DAT20 NYC folder. And so when I say pandas.read CSV, I'm going to read this locally. And I'll comment this out because it's not quite part of the lesson, but just to make a note, this is how to see your current working directory. What is called the CWD. And this is always available in Python. It's always good to be mindful of what your current working directory is so that you know where to load relative files to. It's a common source of error. Now I'm going to read this again. This CSV file is in DAT20NYC/data. If I do read CSV and I have to go up a folder. So again, this first two dot slash is going up to lectures. Then I go up to DAT20C, and I do data. And I can always press tab. And this is always a good trick to navigate your files, that you should be able to press tab, and it should be able to get autocomplete. IPython's pretty good with autocomplete. But this is also true in the Unix terminal as well. I always sort of get in the habit of using autocomplete to navigate between files, because there's just no way I'm ever going to remember like which all my relative files in the path. So it's just a way of making sure that the tab complete's not only convenient, but also just make sure that you're where you think you are in terms of the repository. I'm going to load the advertising.csv. I'm going to call this advertising. And I load that, and I'm just going to preview it using advertising.head. And sort of annoying, yeah. There's an unnamed column in here. And I believe that actually came from the formatting of the CSV itself. I'm just going to drop that column. And just say advertising.drop unnamed, and I have to be exact. And if I drop that and I call advertising again, and I say print advertising.head, I still have unnamed. And the reason is because pandas in most cases by default, if you call any sort of function on a data frame, it will not internally modify. Pandas by default returns what's called a defensive copy of the data frame. In other words, it copies it so that you don't accidentally corrupt data or overwrite data that you might want to use later. So I'm going to explicitly say advertising equals advertising.drop in the column name. And what this does is it replaces advertising with the return value of the drop function. It returns a data frame without that column. And, oh yeah, I have to say axis equals 1. Axis equals 1 refers to my columns. And got a duplicate. Oh, I'll call it twice. So now I have my advertising variable, and it's clean. It has the exact data that I'm looking for. And first things first, I am going to, if I look at the, I'll sort of keep this for my reference. By the way, IPython always will try to output the last value that you enter. Sometimes this is a good thing, sometimes it isn't. For instance, sometimes I get a very, very large, massive column like this. If you want to not have it do that, just put a semicolon at the end, and it will sort of silence and squelch that output. But for illustrative purposes, I'm going to show advertising dot and get the first 5, call head to get the first 5 rows. And I am going to first visualize that data. So I'm going to say advertising. I have two variables that I want to plot. Advertising. I want to see the relationship between what I'm calling my X variable, which is advertising TV, and my Y variable, which is advertising sales. I want to see a relationship between TV and sales. And I'm going to say plt.figure. This is going to basically create a canvas. If I say plt dot plot, I'm going to plot X and Y. And I get, for plot always plots a line. If you want to see a scatter plot, again, this is the same exact plot that I got in the end of what we used in last class's example.
Any way to change the colors?
Yes. If I want to change the colors of the markers, there's basically the first 2 arguments. If I look at the signature of the scatter function, because this X and Y, these do not have a default value. In other words, they're required. So scatter always needs to take a X and Y. But if I look at the parameters after that, I get a bunch of parameters. And there's one here called keyword args. And that's basically what we call variable arguments, which act very much like it's basically additional arguments that get passed along to a function within scatter. If I wanted the C, there's one parameter here called C, which is my color. And you can see by default, it defaults to B, which means blue. If on the other hand, I overwrite that default value, give myself a little more space here. I can say C equals R, and you can probably imagine what that's going to do. Changes my points to red. My plot's a little small though. Maybe I want to blow it up. And so I'm going to say fig size equals, and this is the dimensions wide by tall. I'm going to say it's going to be 18 units wide and, I don't know, 10 units tall. What did I miss? Running property fig size. Oh yes, I want to sort of show that so plot is basically the global object that I imported here from matplotlib. And I want to basically define an axis. I'm going to say plt.gca, which means get current axes. And it's going to, since I don't have an axes object yet, it creates a canvas, and I can use the axes object, and I can plot directly on the axes object. So rather than actually plotting directly on the pyplot figure, I'm just going to basically declare a new axes, and I'm going to use that. And I recommend as much as possible that you use the object. There's, unfortunately, matplotlib is a bit, there's a lot of legacy, what you call old code in matplotlib. And I recommend trying to use the object-oriented approach as much as possible. I posted over the weekend a cheat sheet on matplotlib, and one of the first things it goes through, one of the first things it talks about is the difference between the declarative stateful approach versus the object-oriented approach. The object-oriented approach, basically, I'm creating an axes object, and then I'm basically using, just like I call objects on data frames, just how I call objects on anything else, I'm referencing the axes object, and then I'm manipulating it that way. Life will be a lot easier for you if you always try to sort of create figures and plot on axes rather than explicitly using the global plot function. I will say fig size again equals 18 wide by 19 tall. I believe it's subplot, so axes. Here we used a subplot. And I actually have to declare basically a plot first, and then get the axes from there. I'll come back to that in a second. There's a bunch of other params I can use. So S stands for size. That sets the size of my markers. If I use 100, it'll become large. If I bring it down, this is the point size. I can also say axes.grid true. I'm going to turn on the grid. And so already you can see we're basically able to, I can set, there's all sorts of parameters, and I'll leave it up to you to look through the documentation, because you could easily spend a lecture just talking about each one of these plots. But let's say last class we discussed the importance of really defining the mean. I'm going to declare a variable called xmean. And I'm going to say axes, and I'm going to plot a horizontal line. So, in other words, sometimes I want to plot multiple things on one graph, and I want to plot where the mean is along the y-axis. So I'm going to say axes dot ax axes dot. There's a v line. There's AXV line, and there's AXH line. And I'm going to say AXH line, and I want to basically specify the y, the point along y, where I'm going to plot that line. If I said y equals 5, it would plot a simple line along 5. I want to plot it along the mean. So let's, whoops, I meant y main, didn't I? So I have now a horizontal line along the mean, and it's sort of obtrusive. I don't want it to overlap my points too much. I'll lower the opacity because it's kind of hard to see on the slide how the opacity works. But I have this opacity, and AX line acts a lot like a all of these plot functions generally take similar sort of arguments. I can say marker style, or I can say line width equals 3. So I can change the line width. Here I can also say line width. So I can say line width equals 10, and I get, that controls the border of my points. Say line width equals 1, line width equals 0. I think by default it's 1. I'll leave it at 1. And there's also line, I believe it's line style. So there's all sorts of, the argument that I pass to line style, if I want to get dotted lines, I can put dash dash to get simple dashed lines. If I want a thinner dot, take this down to 2. If I want a thinner dot, I can give a colon. I can also do a dot dash. There's it? It's dash dot. I can do dash dot, and I can sort of define an intermediate dashed line. I'll leave it with the double dash right now, and this is the mean of my data set of all the points along y.
What are the opacity here? Is it just showing them the different data points so you can see them better?
Yeah, so for this case, I just use it for illustrative purposes, but for very dense data sets, like the bike share data set, sometimes incur an issue what's called overplotting, where there's multiple plots because the density of information is so high, the points will overlap each other. And so sometimes you can get around that by reducing the alpha. You can see here, for instance, there's a bit of overplotting here in this sort of bottom left corner. And so if I set the alpha, it sort of communicates that density a little better. If I turn it back up to 1, again, you have plots overlapping each other and doesn't really show the data as well. And I'm going to, again, on that point, I'm actually going to prune my number of samples down. So right now there's 200 samples on my plot. I am going to limit, I'm going to sort of cut the size of the samples down. I'm going to say, and I'm going to plot 20 samples, just to make so I don't clutter my plot up too much. And I'll do that with advertising head, and I've just declared a variable that's basically n samples. We use capital N by convention to indicate the number of samples we have. And if I plot that now I have a much more sparse data set. And yeah, so I just called advertising.head, and I passed n. N is 20. So I'm just first showing basically the first 20 data sets, first 20 points in my data set. I'm going to reduce the AX line size, and again, these plotting functions have similar arguments. So I'm going to call this the color of this one. I'm going to make the mean line magenta. Maybe it doesn't take magenta. I think it's because of colors. It's consistent except when it's not. Oh, there's a comma. Yeah. So I've shown my mean line, I've shown my data points, and again, I want to show the sum of the residuals of the mean. In other words, I want to define really how much my data set deviates along the y-axis. There's a function called v-lines and h-lines. And what v-lines lets me do is it lets me plot vertical lines between it plots lines that share the same x value between two sets of points along y. And I'll start by passing in my x vector. And I have a y min and a y max. So if I just say x and let's say plot between 5 and 20, then you can see I'm plotting vertical lines, and each of those vertical lines coincides with a point. But I need to get them so that they're going between that specific point and the mean. So I'm going to, for the first point, I'm going to just say y mean. And for the second point, I'll say y. I'll give you guys a second to keep up. But is it clear how I got that? is it clear why, I mean, more importantly, speaking of my point earlier, are you guys clear why I'm trying to look at the sum of these points here?
Yeah.
I'm basically defining sort of a variance along y. So the sum squared of each of these lines, the sum squared length of those lines, if I divide that by the number of samples, if I sum them all up, if I sum the squares of all of them, and I divide them by the total number of samples minus 1, I get the covariance. And we need the covariance, that's part of how we define our beta term. So again, I don't want to clutter this plot up too much. I'll say line style, and I just want that sort of thin dashed style, and I'll say alpha equals, let's do 0.3, and I'll say color equals orange. It's a little bit too faint. Maybe orange isn't the best color. Let's do pink. Maybe pink isn't the best color either. Let's do blue. So great. Done some basic plotting. I have a line. I have a point. Let's find a regression line. In the before class example, the one I sent out yesterday, we were using stats models, or in last class we were using stats models. In the pre-lecture, I introduced a tool called scikit-learn. And scikit-learn is going to be another major tool that we use along with pandas for a lot of the other stuff in this class. I'm going to say from sklearn, I'm going to import my linear regression model from sklearn. Sorry, linear regression is an object. sklearn. Forget the exact name for it. I think it's linear regression. Yeah, it's linear model.linear regression. So basically what I'm doing here is I'm declaring, the first thing I do is I'm within scikit-learn, I'm declaring an object called regressor. And this regressor is just an object that's going to, it has a variety of methods, but the first thing it does is I can call this fit function. What fit does is it fits my predicted value, my y, to my explanatory value, x. And by the way, before I go any further, I'm going to add labels. I'll say set title. It's always important to set your title and your labels. I'm going to say sales versus TV advertisement spend. And on axes dot, I'll say set x label. I'll just put TV advertising spend. And on y label, I will put sales. So great, we've labeled our axes. I'm going to increase the font size a little bit here. I believe it's font size, just font size, yeah. It's a little large. Bring it down to 18. And yeah, I can call fig size. So before, when I call fig size on figure, figure is basically stating, it's telling matplotlib, or sorry, pyplot within matplotlib, which is my PLT object. It's saying create a figure with the default size fig size. When I call plt.gca, I'm creating a new set of axes. Axes are the canvas, they're the object, the context on which I'm plotting. And again, because I can call, once I have the axes object, this is, by the way, I recommend this sort of pattern of doing things, of creating the axes object and then using the axes to plot. I just want to reiterate that and make that clear. I can, because once I do that, I have flexibility in creating multiple items, multiple plots on the same set of axes. And I'll make this a little larger. So I made the plot larger. I'll make the points larger. Maybe it'll go up to 150. And since I'm not overplotting now, then I can set the opacity to 1. So we have our line. We have our basic graph. And again, I want to define, call this step 2. Step 2. Define, what am I defining? I'm defining beta 0 and beta 1. I guess I'll be clear, I won't say define, I'm deriving beta 0 and beta 1 from a set of points in x and y. The fit function, again, takes two variables, x and y. And x, again, is the TV advertisement spend. Y is sales. And when I call fit, what did I miss? Tuple index out of range. When I fit my data, basically I get back a set of parameters, but chief among them are the my x and y variables. Oh, the error that I just got here is sort of something very, very useful, and you might encounter. This index error, tuple index out of range, it's a very vague error because this tuple index out of range is actually an error within the Python tuple object. It's not actually being triggered at a high level with the fit function. But what I need to do is create sort of an artificial axis. And so if I plot y, right, if I'm here, if I reevaluate my previous cell, and again I have to make sure that I'm not contaminating if I run this more than once. But if I print x.shape here, and I print x.shape here, if I say x equals x np.newAxis, what I'm doing is I'm sort of creating an additional dimension, a blank dimension. And so before it was a tuple, now it's a NumPy tuple that explicitly has 20 rows and 1 column. So it's sort of turning it into a matrix from a vector. And I have to do that here in order to get scikit-learn to play along. And it's kind of annoying because it's not necessarily obvious that you need to do that. But if I run it multiple times, again, this is sort of why you have to be careful running cells more than once. Why am I getting an error? Look closely. Every time I rerun the cell, I'm overwriting x. And so this is what we call being careful on how we mutate objects. I'm just going to put this here for now and say I'm not going to change x. I'm just going to pass. I'm going to add an additional dimension to x. I'm going to turn it into a matrix from a vector, and I'm going to call this fit function. And I have to go back here and reevaluate x. But watch out for that error because it's easy to get tripped up on that. So I have a regressor object and I fit x and y. And what I get back is I get a set of parameters that are my coefficients. I have one coefficient I have a coefficient, which is my beta 0, and I have a y-intercept. Give you guys a second. I'm going to shrink this down a little bit. What is, geometrically, what is this number, well, what does this number represent in my model? Yeah, and what's this? Yep. So if I have the slope and the y-intercept, I can plot my model, I can plot my line. And again, I'll do that again on this axis object. And, well, I'll define the range. So I have x min, x dot min. I'm going to define basically the range over which x is defined. Or I guess the domain over which x is defined. And basically I want to plot this line. I want to overlay this line on this plot. Or something like it. And so if I say axes dot plot x min, so if I pass a pair of arrays to plot, and I say, oh, I don't know, let's say x is 3 and 5, and y is 5, is 4 and 9. I'm going to have to create a new figure here. Because my figure is being referenced here, it's sort of a quirk of IPython. It's sort of referencing, it's trying to plot an object, but it's not actually creating it because it's already created it here. I'm going to create a new figure. And I'll make it a little smaller. And I will say plt.get current axes. I'll say axes regression. If I did this right, I get my regression line. Well, sorry, not my regression line. I just plotted from 3 to 5. Again, I'm going from 3 to 5, then 4 to 9. So plot just takes a pair of vectors. My domain in this case is just going to be my x min, right? And my x max. So I'm plotting between x min and x max. That's the extent of my regression. I'm also plotting what's my y? If I say y1 and y2, what are y1 and y2? So I'll give you guys 5 minutes as an exercise. I've given you plot so far, right? I want you to find y1 and y2 and plot y1 and y2. And then I want you to, on the same axes, overlay the points from the previous cell. And these are the 20 points I showed. So let's show the points and the regression line on top. Questions so far? Okay. And then we'll pick up lecture. Actually, we'll give it 5 minutes. We'll pick up lecture in 7:30. By the way, bonus points if you can do it in one line. You should be able to do it in one line of code.
Parameters for a function. What's the keyboard command?
For which? Oh, it's
Shift
Shift Tab.
Shift.
So if I'm like within the signature of a function,
Right.
it's Shift Tab.
I'll write down. What's the command for inserting a line, new line in a IPython notebook?
I believe it's O to actually no, I think it's it's A to do it above. Yeah, it's A to do it above, and if I want to delete that, I would do DD, and then below. You can get to all this stuff by pressing H. If I want to say insert cell below, then it would be B.
So control. Okay.
B. But what I do is I to evaluate and create a cell below.
Oh,
It's
yeah.
Alt Enter.
Just
So
hold out and just.
yeah.
Cool.
Sure.
Not yet. First, I got asked.
Do you have an PLT server?
Yes. So that was my mission.
Do you try to try to put in that copy of the command or that? No, so it's
I think that was
provide the cell
Actually, I was.
Oh, we're here fix this. Look at PLT by figure. You'll have them using that parentheses. And that's a single issue. So scatter with a parentheses as well.
Okay, alright, so just.
Yeah.
Cool, thanks.
Anyone? What? Almost?
We're figuring what the wide value is according to the.
Doesn't matter. Yeah, that's a Python.
Yeah, yes.
Yeah, I know you're something
Oh,
Right? You know?
Needs to be there. Yeah, and you there.
Are you getting there or is it getting result? Okay, no worries.
Okay, let's review. So my approach was to, I have a vector x. I actually plotted the x and y along the point for every defined value of x. So I have a list of x values, right? So if I do, if I print my x value, I have a bunch of x values, and I just want to plot those. I just sort of want to sort of see along my line where those x values intercept with my line. I'm going to shrink this a little bit so it's not keep scrolling back and forth. And we'll squelch this out a bit. I'm going to make each of these points along the line here. Well, actually, before I do, sort of show you, I have x, and I'm multiplying each value of x by my coefficient. Z. So I have x, and for each value of x, I'm multiplying it by my coefficient, which is my slope, and I'm adding regressor.intercept. np.multiply is just sort of a form of doing multiplication on vectors. Python by default doesn't multiply things in the same way that other languages do, depending on where I put my variables. So if I do x times x is a vector, it can sometimes give me, it'll sort of act like an array. I always use np.multiply when I'm multiplying vectors. I just like to get in the habit, because in Python, what's confusing is if I have an array, right? And if I say 3a times 3, what do you think I'll get? I get a repeated array. So NumPy has this np.multiply function, and I prefer using it just so I don't get confused with this notation here, because this has burned me a few times where I, get different size vectors, or if I it's not always explicit that a times b will give you what you think it will in Python. So that's why this numpy.multiply exists. Anyhow, what I've done is I've basically said multiply my coefficient times my independent variable and add the y-intercept. Look familiar? It's just this. This is, in this example, my regressor.coefficient. That's there's an underscore at the end, that's my beta 1. My beta 0 is my regressor dot y intercept. The underscores at the end of each of those terms means that they're estimates. They're derived values. They're estimates of a model. The reason they're estimates is that what I'm showing here is presumably a subsample of a larger data set. The larger my data set is, the better, the more confidence I have in my estimate, but ultimately I'm still looking at just a subsample of a larger data set. And so in statistics we call these estimates. Everything in statistics is inevitably an estimate. That's what statistics is. It's an estimate of some real world, large scale, larger population. So what I've done is for each value of this, my x vector, I've multiplied it by my coefficient, and I've added a regressor.y-intercept. And this is what I get. I'm going to, so first here I've drawn two things. I've drawn a scatter, which is x and y hat. This is a plot of my model with points along, with points for each value of x. It's a little hard to see, isn't it? So line width equals 1, same marker equals plus, and is it S? So each one of these points here is the specific point, it's the estimated value. So if I were to sample along my line, make this a little larger. If I were to sample along my line, if I were to say, this is my y hat, for every point along here, this is the estimated value that my model gives me. In other words, if you were to give me an x value, if you were to say, I want to estimate the sales at $100 million, I would tell you it's going to be around, say, 12 here. I'll turn the grid back on so you can see it. Make this a little more clear. So if I were to say, the whole point of me having a model is that I should be able to, if my model is good, I should be able to generalize, and I should be able to see, to plot points along this line that are estimates of the true value. And I'll plot sort of my residuals. We talked about residuals last class. My residuals are what the difference between my observation and my model. Each of these points in space is an observation, and in a perfect world, they'd be close to our regression line, but ultimately, depending on how good our regression is, or depending on the nature of our data set, it may be closer or farther away. So I'm going to do this with v-lines, and I'm going to say v-lines along x with y hat as a reference, and is the first point, and do this y as the second. Questions?
Can you please go back to the code?
Yeah, sorry. Need 2 monitors for this stuff. Again, I'll make the plot a little smaller. So what have I done so far? I've grabbed my data set, I've subset part of it, extracted out 20 points, so that's 10% of the entire model. And I used scikit-learn to determine the line of best fit within my data set. Then, given the points I already knew, or given the points in my data set, I plotted those along the line, and I found the difference between each of these points and the line. These are my residuals. My residuals, if I sum up my residuals, so here on this plot, I have all of my residuals. On this plot I showed you earlier here, these aren't residuals, are they? Well, they're kind of like residuals, but they're the difference between the data points and the mean. Again, same data points, different line. This line is the mean. This line is the regression. The difference, the ratio of the sum of the squares of all of these black lines divided by the sum of squares of all of these blue lines is related to my r squared. 1 minus that number is my r squared. So if I say let's paint these guys blue, make this larger. And let's paint these guys red. Well, make them green for ambiguity. So what I've done is I've added up. I've added two things. If I were to say, look at the ratio, sort of use this notation to represent my green lines and my blue lines. If I look at the length of my blue lines and I square it, I look at the length of each of my green lines and I square it, each of my blue lines and I square it. If this value is very, very small, if this goes to 0, this becomes 0. So if I have, in the case where I have a line and my regression points all fit along this line, then this numerator term is 0. It's going to be approximately equal to 0, because these are all 0. If I have, on the other hand, my mean values, the values of my data points are relatively small, and I have a flat line, then this number grows as well. If this number comes down, if my points are very close to my line, if they're very close to the mean, this number becomes small. And so when I'm looking at the R squared, is 1 minus this number. This we call R squared. It's our coefficient of determination. So just to make it more clear, I'll call this the y sub I minus the y into regression squared. We call this y sub I minus the mean of y squared. When R squared is 1, I have a good fit. When R squared is close to 0, R squared is within the domain between 0 and 1. The closer it is to 0, the more close my regression is to just randomness. The better my fit, the closer R squared is 1. But it's always going to be between 0 and 1. Questions? So for this data set, for this n equals 20, I want you to calculate R squared on this data set. And say give it till 8, calculate R squared, and yeah, write it down. You have enough information here, given x and y and all the stuff we've calculated in this previous cell, to calculate both of those, that R squared term.
Okay. And then my big question is, doing the end one, I'm not having that carry through this, it's just in the subset, I get all the pieces. So I'm just going to get this again, but then I'm not sure if it's enough full starts to be interested.
If you reevaluate the cell, right? And you scroll up. You need to say advertising equals head, and that's because
Is it equals?
yeah. So head defends it doesn't actually modify the
That's what I
receiver.
thought when I thought about it.
Yeah. So just say advertising head. Just call it that.
Yes. Thank you.
No problem.
This is a really easy example, so you just go to this overview and just ask you some questions. Got it? By the way, you should be able to do this without using a for loop. It's okay to do it with a for loop first, but it should be possible without doing a for loop. Think about how NumPy handles operations like subtraction and addition. Are you in VCR? Is it running? Yes. Calculate our strength. It's I mean, no, yeah. Yeah, it's trying to put the entire code on that one screen. But this is basically very simple, just like a class exercise. So you have this, so you have pretty much everything, you're just missing the second scatter. There's two scatters up there. So the scatter, one scatter is plot those points along the regression line, and the other scatter is actually plot the original data points themselves. Oh, it's head. Oh, so you can use head. Yeah. And you also just select the first 20, but head just selects the first 20. So if you say data equals data head passes 20, it'll just reassign data with the first 20. No, well, AD data, so if you go to what AD data is, that's data. Right there, we say head. So what head is doing is the function calls is grabbing the first 5 rows. So if you first had said add data, yeah, you add data, you're reassigning add data, but you need to pass in 20, you always get the first 20. So just set n equals 20. You can do it that way. Yeah, that would work fine. But I would recommend declaring it outside of the function call. So you say it this way. Previous line. Well, you need to reevaluate all of your cells. Yeah, you can just do cell. You can also sometimes use like this one.
Have those,
Yeah, you have all this already. Yes, you have
and you have which how did you see that? So it was so then
Yeah, I'm trying to subtract.
yeah, I saw that. But I don't think that's
So you have when you want, so if you copy a scatter,
It's element.
just like I have up there, you should be able to use that given the.
yeah, it's one
We're subtracting the first element.
Did I miss how you selected I'm using the entire sample argument. I missed how you selected
Scroll up.
the subset.
it's the
So if you go to, when you initially define advertising,
so whatever.
Actually, right up here.
So you're doing
Hey, guys.
that, yeah.
Some of you are including the whole data set. I subset to the first 20 by saying advertising equals advertising.head. And I passed in 20. And I'm reassigning, so when I call advertising.head and pass in 20, I'm just reassigning advertising to only include whatever its first 20 terms is. You might need to reevaluate your notebook if you go back and do this, and you might need to reevaluate that cell. Calling advertising.head doesn't truncate the data frame.
If you do np.subtract, and then you pass in, do both series have to be the same size, or do you have one series and then have the second element like act on
on subtraction, if you're right now you can subtract directly from the scalar. So if you subtract a scalar from an array, then it will do that just fine. If you subtract an array from an array, they both have to be the same size. You can subtract a scalar from an array. Questions? So who has R squared? No one has R squared yet?
47.
So don't show it now. It's okay.
You could even, I mean, there's 20 points. You could actually do this with pen and paper if you wanted to. I mean, it might be a while, but not that I'm suggesting you do. But ultimately we can generalize. And so you can imagine if n were very, very, very large, the same operations would apply.